flat plate external flow, and we presented the Blausius solution. And then after the Blausius solution, we looked at the different empirical relationships that were available for covering external flow for both flat plate, or not both, but flat plate, for cylinders, and for spheres. And all of those relationships are contained where? This right. All of those relationships for external flow are contained where?
7.7.
Well, yeah, they're in the book. Where in the book? Pardon me? 7.7. 7.7 is your big external flow table. What is 8.4? Internal flow. And today is the last lesson of internal flow. So what goes on next time? JJ.
External flow?
Did external flow, JJ. Although you are right in a kind of in a way. It is kind of external. What is next?
Radiation.
Man, look at the syllabus. Get your syllabus out. For goodness sakes. It's frustrating. How can you be truly anticipating what you're getting here if you don't know what you're going to be able to anticipate? What? Yeah, I know. It is a surprise. Free convection. And although free convection is primarily external, sometimes we consider free convection internally too. I'm looking at a case where free convection is one of the primary design considerations. What is that? Anybody know? Those windows right there. There's two panes of glass. Usually some sort of gas or air in between. What is the design criteria for the spacing of the two panes of glass? So they're close enough together so you don't get effective free convection cells forming in the window. Why is that? That would facilitate heat transfer. So if they're close enough together that the gas is a dead space, then it's much more effective in resisting heat transfer. If the gas begins to circulate because there's enough room for it, and now you understand all this stuff with boundary layers and viscosity and et cetera, et cetera. So that's one of the considerations why why a dual pane window, for example, is much more effective than the old storm window, which was put over a regular piece of glass. Why? Because the storm window had about 2 to 3, 4 inches worth of room. There was plenty of room for free convective cells to develop and circulate, increasing the amount of heat loss. All right, so today's class is kind of a pull it all together class. Now, I want you to open your books up to table 8.4, and I want you to follow along. I'm going to refer to certain equations, and I want you to go back and flip in your book, and I want you to look at these equations as we go through here, because this is it. We're done with it. You're now responsible for everything in Chapter 8. There's a lot of stuff in Chapter 8. So let's get started. We're going to start by doing a simple energy balance. You'll recall that the heat transfer that occurs in internal flow is going to be, could be expressed as the mass flow rate of the fluid to which the heat is being transferred to or from, times the specific heat of the fluid, C sub P, times the medium temperature out minus the medium temperature in. So if we can measure the temperature of the fluid flowing into a tube and the temperature of the fluid flowing out, and we have m dot and C sub P, we can know how much heat transfer was transferred to that fluid. This has nothing to do with H, but we can also say that this heat transfer is going to be H times the area of the surface at which the heat transfer occurs times the temperature of the surface minus the mean temperature of the fluid. Now, at this point, you should be able to appreciate the complexity of the second equation. What changes in the second equation? Potentially S, Ts, if it's a constant surface heat flux condition rather than constant surface temperature. And what will certainly change? What else will change? Not usually. We're going to normally assume that H is going to be constant over the length of the pipe. Although, you know, we know that it's a little different in the entry region. But if the entry region is not too long, we'll ignore it and just use the H for the rest of the pipe. So what else changes? Tm. We know that that changes as a function of X. Either, for both of our cases of study, constant surface heat flux as well as constant surface temperature, Tm changes. So, you just can't plop a number in here. Now, if you had an average Tm over the whole length of the pipe, then you could do a good approximation for how much heat transfer would occur. Okay? But we sometimes don't have that. All right. So we have two cases, so let's take a look at these two cases. For case one, case number one is where we have a constant surface heat flux. This value is constant. And if that value is constant, then we can say that the mean temperature of the fluid at any point X down the flow of the pipe is going to be equal to T of the temperature in plus Q, the flux, times the perimeter of the pipe over m dot C sub P times X, the distance down the pipe. And this is one of the equations that you will find very useful. And this is equation 840 in your textbook. So open up equation 840. This equation does not occur or appear in your in table 8.4. This is not one of the empirical or otherwise analytical relationships for solving for H. But this is one of the equations that you're going to use a lot to solve different types of problems. So if you want to find the temperature of the fluid, Jake, do you have a question?
Yeah, we can keep going.
If you want to find the temperature of the fluid flowing through a pipe where the pipe or the tube is exposed to a constant surface heat flux, you can use equation 840. What do you need to know? You're going to need to know the mean temperature at the inlet. You're going to need the surface flux. You're going to need to know the perimeter, which is the parameter of the pipe itself, m dot Cp, and the distance down the pipe. Of course, we might ask you, at a point down the pipe, how far down the pipe, how long has the pipe got to be for the fluid? Let's say it enters at 100 degrees and you want it at 150 degrees. How long does the pipe have to be? Can you use this equation to solve for it? Sure. So there are different ways to ask questions using this basic relationship. Very important relationship you're going to use on the exams and in your homework. Okay? Now that's case number one. We also have to look at case number two. Case number two, of course, is constant surface temperature. All right? So we have constant surface temperature. All right. As you know, when we have constant surface temperature, Ts remains constant, but we have a non-linear change in our mean temperature. So what we end up with is the following relationship. Temperature of the surface minus the mean temperature at the outlet over the temperature of the surface minus the mean temperature at the inlet is equal to E with an argument of minus PL over m dot Cp times H bar. And this is equation 840. 841B. And you're going to use this quite a bit. You can also make a slight variant of this. Very useful by saying, okay, I want to know what the temperature is at some point down the tube. And this is equation 842. Now these equations, these three equations, pardon me?
Why is it not each bar in this?
I'm sorry, these equations, these three equations are very, very useful. Brendan, do you have a question?
The book has H bar inside the exponential.
Can't hear you.
The book has H bar inside the exponential for the equation.
For 841 to 842.
Yeah.
You just change inside.
Better?
Yeah.
You're absolutely right. All right. These three equations are going to be very, very useful to you when you're solving for different properties. As I've already indicated, we might ask for the mean temperature, we might ask for the distance, a little more complex, but we can ask for the diameter of the pipe or the related to the mass flow rate. There's a lot of different things you can solve for, so these three equations are very useful. Now, of course, they're all going. These two equations here require the H as well. This one does. So let's take a look now at continuing this discussion about the constant surface temperature. All right. This is a little more complicated. Because of the nonlinear nature T sub n. So in other words, if you'll recall back to when we first discussed this back about 3 lessons ago now, we drew the 2 pictures on the board, and the pictures are in your textbook. Let's go to those for a second. On page 503 of your textbook, figure 8.7b. And you'll notice we talked about the fact that in that case Ts is of course constant, but that Tm is non-linear. Okay? And I also made a point of showing you when we drew that picture on the board that we refer to the delta at the inlet as delta T inlet, and the delta as the exit is delta T outlet. Okay? And we're going to use those to help us calculate and approximate the heat transfer. So we're going to let Q convection, we're going to define this as being equal to H bar times the area of the surface times delta T. We're going to subscript this Lm or what is known as the log mean temperature difference. Okay? The log mean temperature difference. And this is equation 843. Now, we're not going to use this for constant surface heat flux. Why wouldn't we?
There's not an exponential difference.
Yeah, but there's a more basic reason than that. We know what the constant surface, typically we're given a constant surface heat flux. Right, that's the condition. But you're right, I mean, it's not. And we could find it out by several different ways of solving for that. But typically we're given the heat flux in the case of the constant surface heat flux. So we're not solving for it. Here we're solving for the amount of heat transfer. We're going to have h bar, a sub s, and the log mean temperature difference. Yes, Austin?
I was just wondering what that subscript was, but you
That's
said it.
Lm,
Okay.
log mean. Okay? And where Lm equals the log mean temperature difference. Okay? And it is defined as the difference between the temperature at the outlet minus the difference between the temperature at the inlet over the natural logarithm with an argument of the delta of the temperature at the outlet divided by the temperature at the inlet. And this is equation 844. And by the way, you can reverse everything and get the same result. So the log mean temperature difference can be the difference between the temperature at the inlet minus the temperature at the outlet divided by the natural logarithm with an argument of the delta of the temperature at the inlet minus the divided by the temperature of the outlet. Okay? So you can flip-flop that, get the same result. So we're going to ask you to solve for this occasionally as well. And by the way, we're going to use this in our heat exchangers quite a bit. All right. So these are all equations that you're going to need to manipulate, solving problems on the homework and on the exam. Any questions? Let's take a look now at Table 8.4. Okay? Table 8.4, if we look at it, we have discussed the correlation for the friction factor for laminar fully developed flow. We have actually gone through the development of the Nusselt number equal to 4.36 for laminar fully developed flow with uniform heat transfer coefficient, with uniform surface heat transfer. You were given the fact that the Nusselt number is equal to 3.66 for laminar fully developed flow with a uniform TS. And then we talked last time at the conclusion of the class about the next two equations, 857 and 858. Let's talk about those for a second. If you look at these two equations, these are both for the entry region. One of the good things about Incompare and DeWitt and Levine and Bergen is that Incompare and DeWitt really searched out and got some of the best heat transfer correlations that were out there. And these two equations, 857, look at the conditions: laminar flow, thermal entry length, or combined entry with a Prandtl of greater than 5, a uniform temperature at the surface, and then this, I forget the, if you go to table 6.2, I think it's in there, the GZ number. No, it's not. It's in your book, though. I forget what the name of that is, but it's just a combination of the Randall and the Prandtl number. And let's go back here to the entry region, page 514 in your text. Okay? Now, if you look at this, 857 is on page 515. The value for this GZ number, the Gratz number, is up above that in equation 856. Now, I'm not going to write these down. You're not going to use them this much. But you should know that they're here. You can also use the figures that are shown in 810, if you'd like. 810 shows, 810A shows the thermal entry length as well as the combined entry length, but these tables, this particular figure is restricted for a Prandtl number of 0.7. So if your Prandtl number is significantly different from 0.7, you may want to consider using the equations 857 or 858 rather than this, because you're going to get some significant error. All right, and then if you want, you can use figure B for combined entry length, and it shows you the two equations, 857 and 858, and it shows you the approximate placement of the lines, the shifts in those lines for different Prandtl numbers. I think the easiest way to do it is just simply to calculate the equation if you really need it. Because these tables, these figures are so small, if you need to use them, it's going to be hard to do it. Okay? So you have 857, which is predominantly for thermal entry length problems. We want to find the H in the thermal entry length. And 858, which is for both combined entry length, thermal entry length, as well as the hydrodynamic entry length. Okay? Now, admittedly, I'm not going to typically give you a lot of problems in this area, but you should know that these are here. So let's jump past that for a moment, and let's look now at the next equation. Excuse me. You recognize the transcendental equation, which you may have used in your homework solution to solve for the friction factor for turbulent flow in pipes. It's this equation that the Moody chart is based on. It's easy enough to do it if you have the inclination to do so, or you can use the Moody chart. If we have a tube that is defined as a smooth wall, the friction factor is shown in equation 821. So that brings us now to the next two, and you use that equation as well in your homework assignment. So that brings us to the next two equations. And these two equations are the equations which you are probably going to use most of the time. Very seldom, frankly, do you encounter in real applications laminar flow. It's just too slow, way too slow. It's barely creeping along. Vast majority of pipe flow, especially from a commercial and practical application, is turbulent flow. So that means you're going to use the Nusselt numbers. That are the two equations called the Dittus-Boulder equation and the Sider-Tate. These are worth writing up on the board. These are your turbulent flow go-to equations.
Is this just a constant temperature?
Going to talk about that in a second, okay? Yeah. We're going to talk about that in just a second. Good question, Darren, but hold it. The Dittus-Boulder equation is the Nusselt number. Notice that I don't have a bar on it, by the way. The Nusselt number is equal to 0.023 times the Reynolds number, a function of d, to the 4/5, and the Prandtl number to the n. And this is equation 860. And then the next one we're going to talk about is the Sider-Tate equation. The Sider-Tate equation is the Nusselt number function of D equal to 0.027 times the Reynolds number to the 4/5 times the Prandtl number to the 1/3 times mu over mu sub s to the 0.14. This is equation 861. All right, these are the two equations that you're going to use to solve for the H value. And what are you going to do when you have a problem? The first thing you're going to do when you encounter a two-flow problem is what? Dylan? What?
Number.
Do the Reynolds number. If the Reynolds number is greater than 2300, yeah. Now, if the Reynolds number is really greater than 2300, and it's really turbulent, how far do you think the entry region is?
Really small.
Very, very teeny. The bigger the Reynolds number, the less the Reynolds number. All right. If you have a Reynolds number of 3,000, 4,000, in practical terms, you probably should calculate the entry region as well, because it may be pretty long. All right? But normally for turbulent flow, as we already know, both for the hydrodynamic as well as for the hydrodynamic as well as the thermal entry regions, we're talking an entry region which is usually at most about 10 times the diameter of the pipe. So that's not very long. Okay? All right. So, a couple of thoughts on these. Both of these equations can be used to approximate the average Nusselt number for the pipe if L over D is greater than 10. In other words, you're in the fully developed region. Okay? Both of these equations can be used to this. Now, let's take a look at these equations for a moment. So go to your book, and then also open your book up to page 816. Excuse me, 516 in chapter 8. All right, look at the conditions for the Dittus boulder. Turbulent flow, fully developed. Prandtl numbers of 0.6 to 160. If you're a little below 0.6, not the end of the world. There's nothing else really out there anyway, so you got to use it. You're not going to get above 160. Reynolds numbers is best when the Reynolds number is above 10,000. That sounds like a lot, although you know from your homework, it's not hard to get a Reynolds number of 100,000, 500,000, very easy when it comes to pipe flow. Okay? So Reynolds number of 10,000 is just 4 times the mass flow rate for laminar flow. All right? This is for the fully developed region, L of D greater than 10. Now look at this. The value of N for the Prandtl number, this is important. The value of N for the Prandtl number is 0.4 when the surface is greater than the mean fluid temperature. In other words, when you're heating the fluid which is flowing through the tube. Notice in the next sentence, N is equal to 0.3 when those conditions are reversed. When you're cooling the fluid, that is when the surface temperature is less than the mean temperature. All right? And let's go down to, and let me just say this. In general, the Dittus boulder is for smaller temperature variations. If you go to page 516, you will see equation 860. It talks in the paragraph above that with about the conditions which I just went over that are highlighted in table 8.4. And then below, you will see where the parameters or the exponents are discussed again. Okay? So those are worth highlighting. And then the other conditions are given. By and large, the Dittus-Boulder equation is used for smaller temperature variations. That is, fluid temperature changes of 10 or more, or around, no, excuse me, now I'm getting confused. I'll have to give, there was a specific, one's for gas and one's for, well, let me leave it right there at the same point the book does, and I'll get back to you in next class, because I know that I have it written down somewhere. Smaller temperature variations. But, that being said, I'm going to expect you to use the Dittus-Boulder equation unless I specifically put in the problem statement large temperature variations. Take those into consideration. If there's large temperature variations, then you will use the Sider-Tate equation. And in the Sider-Tate equation, you have the last term, which is the viscosity ratio. The viscosity in the numerator is evaluated at the mean temperature. And by the way, the properties for both the Dittus-Boulder and the Sider-Tate equation are calculated on the mean temperature, the average mean temperature of the flow, or what you're going to estimate to be the mean temperature of the flow. Now, I'm not going to give you a problem like this in class because it's too confusing. But in real life, sometimes you're not going to know what the temperature is going to be coming out of the other end. So what you're going to have to do is you're going to have to take an educated guess at what the temperature is coming out the other end of the pipe. So you're going to take that temperature, and then you're going to have your inlet temperature and what you think is going to be the outlet temperature, and you're going to do a mean temperature on that and say, okay, I'm going to think this is my average temperature. Then I'm going to back off and do all my properties based on that estimate. When you finish the problem and you actually solve for the outlet temperature, what are you going to do?
Compare it to what you did.
Compare it to what you did. This is very important, by the way, if you're actually designing something. You're going to compare it to what you did, and then if it's way off, you're going to go back and redo it.
So it's actually transcendental equation.
That's it. It's an iterative type process in that case. Because unfortunately, it's just the way it is. These relationships are very sensitive to temperature variations. Okay? So, relatively small temperature variations and temperature variations and how they influence the properties, the Prandtl numbers and what have you, and all you have to do is look in the book and see how quickly the Prandtl number changes for the temperature, and you can see what I'm talking about. So you'd go back. Now, in tests, I'm not going to have you do that because that's not the sort of thing you can do in the exam. It's just too time-consuming to do that in a 15-minute exam. All right. Now, I think it was Darren that asked the question, are these for constant surface temperature or are these for constant surface heat flux? I want to direct your attention to page 517 underneath the Sider-Tate equation. Oh, and before I get there, in the Sider-Tate equation, the denominator, the viscosity in the denominator is evaluated at the temperature of the surface. Okay? That's why it's given the subscript S. And it says, where all properties are evaluated at Tm except for mu sub S. To a good approximation, the foregoing correlations, that is both Dittus-Boulder and Sider-Tate, may be applied for both the uniform surface temperature and the constant heat flux conditions. Okay? So you can use them for both. So these are your go-to equations. Any questions? And remember, you're going to use Dittus-Boulder unless I tell you you've got large temperature variations. And that's the key word to jump you in, which Ian and Greg Loeb and Glosser will not know. All right? And do not share it with them. All right? That's a cut of minus 75 points on the test if you use the wrong equation. You can tell them it is. All right. All right. Any questions? Oh my. All right. We're. I don't know why I'm talking so long today, but Okay, open your books and we're going to review the last couple of points here in the last 3 minutes that we have. I want you to go to the entry list. I want you to go to equation 8.3. These should be highlighted in your book because you're going to be asked to solve for these and you need to know where to look for them. All right? Equation 8.3, page 491. That is the laminar flow hydrodynamic entry length. Should be highlighted in yellow. You should be able to go to it right like that. Look down below it, equation 8.4. It is the entry length for the hydrodynamic entry length in turbulent flow. And remember, we discussed it for the purposes of this book. Next sentence down, we're just going to assume that's L over D is greater than 10. Okay? All right, that's the hydrodynamic entry length. For the turbulent thermal entry length, go to equation 823 on page 496. This should also be highlighted in yellow. Notice that that is the same value but multiplied by the Prandtl number for the thermal entry length. And the same condition is highlighted in the text below. The same conditions in the text below, in the paragraph below, the last sentence, for the thermal fully developed entry length. Okay? Now, for turbulent flow. You gotta know these. Now, I haven't wrote them all on the board when we did in class. For the purpose of review, you gotta know where these are in the book, because you may not be able to find them quickly in your notes. So, somehow or another, you should be able to go to these quickly. All right. We talked about the entry length solutions to some length already. And the last thing I want to point out is equation 8.6 and 8.66. 8.6 is a very useful equation. It's at the top of your book, top of the page, on page 492, and is the Reynolds number expressed in terms of m dot. It's a quicker way of solving the Reynolds number than having to solve for the mean velocity. Okay? This is an equation that's worth being highlighted and underlined in red because it's one you should use a lot. Okay? The Reynolds number expressed in terms of m dot. A valuable equation to use when you're solving these problems. The next equation, which I suggest you have handy, is equation 866, which is on which is on page 524. Many of you on problem 7.51 blew it, okay? When we came up with the hydraulic diameter on that problem, all right? You assume the hydraulic diameter for the shapes were the same, or the Reynolds numbers were the same for all of them. They're not. So you've got to calculate the hydraulic diameter, and this is the hydraulic diameter equation. You saw this before for internal flow in chapter 7. For external flow. You have this also for internal flow, and that's equation 866. So, we're going to talk a little bit more when we do our review coming up, but I want you to take a look at table 812. These are all different configurations for fully developed laminar flow, and each one of these configurations there is a constant value of the Nusselt number, and those constant values of the Nusselt numbers are shown right there. And these Nusselt numbers are all calculated on the hydraulic diameter, which is equation 866. Now, it might be useful in your homework. Any questions?
So when do we use the hydraulic diameter?
When you use the hydraulic diameter when you're not using a circular pipe, okay? For non-circular tubes is when you calculate a hydraulic diameter. Sorry. All right, any questions?